look at an example. Suppose I have a solenoid. So current I. We know from Ampere's law that the field inside is given by mu naught and times I, where n is the number. Suppose I have for this example, suppose I have n winding, total of n winding, and this length is L, and the area, cross-section area A of the solenoid. So I want to calculate the self-inductance of this coil here. So let's calculate the flux per turn. So that will be just a B field. Ignoring all the French effects. So let's assume the solenoid is long enough, and I can just, the effect at the top and at the bottom is negligible in that flow effect. Right? And then the flux then is just V times the area. Right? Then it's just mu naught. And that's why N is a total number of winding divided by the length. And the L times I times A. Right? Okay. But the total flux over all the winding is then just equal to n times the flux per turn, then it's just mu naught n squared over L. Okay? So the self-inductance then, oh, I have to say L. Let's call it something else. What did I call it? I call it L also. There's no L here. Let's call it T, right? No, is T right? Yeah. Let's call it T. Okay. And self-inductance. Call the EMF of a loop because of Lenz's law, right? If you change the current in that loop, right, you get the back EMF. It's the back EMF. And if you look at that formula, E, then the inductor is given by mu naught inductance, self-inductance. It's given by mu naught n squared over T times A. That's all. Question on this?
Is that n a little n?
That little n, the magnetic field inside a solenoid is given by mu naught times the number of windings per unit length.
Oh, I see. So those are supposed to be.
But here I'm considering, because I'm actually calculating the self-inductance, so it's a quantity that varies with the size. So I have to actually explicitly write down the number and the length. Right? The flux per turn is just the magnetic field times the area. But if I just calculate over all the turn of the solenoid, then you just have to add up all the flux. So that's why I have to multiply by n, right, to the n terms. Right? So then the total flux is proportional to n squared. Okay. And this is the formula for the self-inductance for the solenoid. This is ignoring all the French effect. So let's consider the solenoid to be really long, right? So the French effect is negligible comparatively. And
DIT there, that's the change in current,
Right,
right?
that's a change in the current.
Okay,
Yes.
and then L
Right,
times DIT.
right. I guess I should probably write that more carefully. The total flux, this is mu naught n squared over dA times R. Right? So, flux T, and it's just this quantity times DIT. Right? Because this is all constant. Okay?
Yeah.
Okay. Questions so far? Any question? Okay. So let's see. With that, so with that in mind, let's just actually do a simple calculation on an LR circuit. Remember, when we talk about capacitors, we have a RC circuit. Here, with the inductor, in this case, an inductor made from a solenoid, but it can be made from, in the book actually, instead of talking about solenoid, Purcell talked about a toroid, right? But I didn't want to. We didn't do a calculation on the B field of a toroid. You should actually look in Purcell and look at that derivation. A toroid is basically a solenoid that you bend into a donut-shaped object, right? And you can calculate the B field. The B field is not constant, but you can actually do it. It's derived in chapter 6, and Purcell used that as an example for an inductor, right? But it's easier to just talk about a solenoid. Here, let's look at an LR circuit. Suppose I have the battery, switch, right? Resistor R, and inductor, right? L. So this inductor can just be that solenoid. Okay? And let's look at what happened when we close the switch. So what happened when you close the switch, the current started to flow, right? And when current flow, you have a back EMF. Let me actually draw this differently, just to make it a bit more obvious. At t equal to 0, close the switch. While in the past, when you close the switch, current immediately rise up, right? There is a step function in the current. It's a function of time. See? But here, because of the inductor, that's not going to happen, right? The inductor acts as an inertia for the current. So what happens is, as you suddenly increase the current, there is a back EMF, right? So let's look at the Kirchhoff law. So this is non-inductor. Kirchhoff law. Then what happened here? This battery or this demon has voltage V, right? And as this is the direction of positive current, right? So when I close the switch, there is a back EMF, right? Just like in the past we define a voltage drop IR, here there is also a voltage drop because of the back EMF, right? And the sign is the same sign as IR, right? Because I define it in such a way that if this is increasing, there's a back EMF there, right? It's like this positive voltage, right? And this positive voltage here, IR is actually along in that direction. So this is minus the back EMF, back reaction of the inductor, minus IR, the usual IR for the resistor, equal to 0, right? So V minus L didt minus IR is equal to 0. This is the Kirchhoff law for the LR circuit. Okay, so let's try to solve for that. Let's solve for the current. And if you look at that equation over there, then you have di equal to 1 over L naught E minus IR. Okay. Rearrange the equation, put all the I on the left hand side, and di over V minus IR is equal to 1 over L. And integrate both sides. From current equal to 0 to final current, right? And from 0 to final. Okay. And when you do this integral with the right kind of substitution, this gives you a log, right? I didn't write it down exactly, but you will get the when you solve this equation, you get the current as a function of time. Then is equal to V over R, 1 minus E to the minus T over tau. Right? And tau here is a time constant. It's given by L over R. Right? This is the equivalent, just like in RC circuit, you have a time constant of RC. Here, in the case of inductor with a resistor, time constant is given by L over R. And it looks like this. So instead of a step function as before, right? That is something that's softer, right? And the time constant here, the 1 over E time constant. Now, it's just this part here, and this is just okay. And notice what happened, right? As you close the circuit, after a long time, everything is just steady state. You have a constant current, right? There is no change in current anymore. So dIdt is 0. If you just differentiate that equation, you'll get dIdt equals SE to the minus E over tau. Right? After a long time, the change in current completely goes away. You have a constant current, right? And this the inductor acts like a short. Right? So when there is no more variation in I, this acts as a short. This is just a wire, right? There's no back EMF anymore, right? So what you have is just a battery and a resistor. Okay? So the current becomes just V over R. Here this becomes V over R. Okay. So just remember, after a long time, there is no more back EMF, and then the inductor becomes short. Okay. Is it clear so far? Any question? No question?
What did you mean by dIdt equals e to the negative t over tau? Because doesn't that like become close to 0? Or?
Yeah, when time goes to, so let's draw it somewhere else. So if I take that equation, right, I as a function of time, I differentiate like t over to like that. And I get the first part here is 0, right? So I have a v over r and 1 over tau e to the minus t over tau. Right? And tau is just L over r, so this becomes v divided by r, and L over r is not cancelled. And v over L e to the minus t over tau. Right? That's dIdt. So what happened is that the rate of change of the current as a function of time drops as an exponential. At time equal to far away, after a long time, then this goes to 0. There is no more change in the current at a long time. Just the inductor acts as a short. And when the inductor acts as a short, then you know that then the current is just V over R, right? Which is just that, V over R. Is there anything?
I don't really understand that bit on the graph that you labeled that you said was the time constant. I'm not quite sure like
Yes,
which part you're labeling.
Right. Just qualitative labeling, but let's see. But you know that if I have an exponential decay, right? If I have an exponential decay, minus t over tau, say, right? When t is equal to tau, right? Then this function here, this function y, say y is equal to e minus t over tau, then at t over tau, y becomes 1 over t. Okay? It becomes e to minus 1. Okay? So this means that this function already dropped to 1 over e of its original value. Okay? And that happened. 1 over e is about 1/3. Right? So this happened around here. Right? It's about 1/3 or 1 over e. Right? And this t is equal to tau. Right? And this is called the time constant. Right? And if you look at this curve, it's just an inverted version of that curve. Right? Because that's just 1 minus the exponential. Right? And the time constant is defined appropriately in the same way. Okay. Question on this? Okay. So with this, then we can now look into energy stored in an inductor. There are two ways to derive this. Before I do that, let me so after a while, right? If you close the circuit, after a long time, you get a constant current. Right? So what happened if suppose I did this? So after a long time. It's about a battery. And the resistors say there's already current flowing high. Right? At some time in the future, I cut the battery off, right? Kill that, right? And short the circuit. Okay. Then what happened? What happened is you look at the Kirchhoff equation, then what you have is instead of 3 minus L di dt is minus IR is equal to 0, right? What you have, if V goes to 0, what you have is just L di dt plus IR is equal to 0. With the boundary condition, I'm redefining time equal to 0 as the time. So let's rewrite the time. Right? The time t equal to 0 is when I remove the battery and short the circuit, right? Okay. So at time equal to 0, I is equal to V over R. Right? And what happened is that if you solve that equation with the right boundary condition, you will see it's the same differential equation, right? Except it's actually homogeneous, not like that one. Then you'll get that I as a function of time becomes V over R into minus T. Same tau. Tau is still L over R. So what happened is it goes like that, right? And this is the first part. this equation, right? And then I define the zero of time, right? I call this the zero of time. Here, I kill the battery, short the circuit, and this is the voltage here. And this is V over R, and this goes as e to the minus t. I'm redefining t equal to 0 to be over here. Okay. So let's look at what happened here, right? When I remove this. Okay. Current still flow for some time, about time equal to tau, right? And then you actually dissipate energy. Right? How much energy do you dissipate? E dissipated. Right? This is just equal to basically Joule heating of the resistor, right? So what is that? The power dissipated in a resistor goes as I squared R, right? But the total energy dissipated has to be integrated over time from t equal to 0 all the way to infinity, right? So I have to integrate this from 0 to infinity, right? And I substitute this equation here. Okay. And when you do that, it's a very simple integration, it's just exponential. You'll find that the total energy dissipated is going to be equal to 1/2 Li squared. So there must be an initial energy stored in the inductor, right? This is energy stored in the inductor. That when I close that circuit, when I short circuit this LR circuit, right, it dissipates everything as Joule heating through the resistor. And at the end of the day, you have nothing because everything is empty. Okay. And then just like an inductor.
So it's stored in Joule heating, or like it creates Joule heating, or like.
The current creates Joule heating in the resistor.
And that's what has
Right.
the leftover energy to dissipate? Or?
Yeah, so there must be something stored inside the inductor first,
Mhm.
right? That when I close the circuit here, right, it dissipates all the energy through the resistor, right? And at the end of the day, you have no more current, right? And all you have is the heat in the resistor, right? Okay. And if you believe in the conservation of energy, right, then the total energy dissipated has to be equal to the original energy. And it turns out to be equal to that, and then we define this to be the energy stored in the inductor.
Is that is that affected at all by how you had the voltage on initially?
No,
Like,
suppose
it
there's
didn't-
already a current in there, right? Suppose I have a steady situation.
So how do you know
there's
that's
already a
from
current flow.
So how do you know it's from the inductor versus from the battery?
There's no more battery here.
But it started with a battery.
It started from the battery, right? And that's what I will do next, actually, a more general consideration. This is
Okay.
actually done by, this is the derivation in Purcell, right? That's what he did. I think he's just using an example to prove a point, right? He's not doing it generally enough. I'll take an extra step further, as you will see. But what happened, this is totally fine, totally general. There's already current flowing. There's already flux in the inductor, right? So there must be some energy stored, right? We just want to know how much,
Yeah.
right? And the way you calculate that is removing the battery, right? And then suddenly short circuiting the LR circuit, right? And then dissipate the whole thing to a resistor.
If there wasn't any current flowing, would the inductor still have any energy stored?
No.
Okay, so it has more
Yes,
to do
yes,
with
yes.
the
Has
current.
to do with the current flowing through the inductor, creating a flux in there,
Okay.
as you will see.
Does the energy stored have anything to do with the fact that there's like a back EMF once you stop?
No, not the energy stored doesn't have anything to do with that, actually, right? Because this is all constant, right? There is already current flowing through it, right? Remember? So I have a circuit with the battery on, right? Turn on the battery so we create current, and the current doesn't actually flow immediately to fuel R. It takes some time to get, right? Because of the back EMF. But after a very long time, after t much longer than tau, right? Basically, all you have is a constant current.
Oh no, I meant like after you switch off the battery or something,
Yes,
then like when it starts slowing down, there's like a back EMF again. Is that like related to the energy
Yes,
stored?
but there is a back EMF again, right? But I'm just calculating, eventually everything will dissipate, right? You lose all the current, right? And they all get converted into molecular motion in the resistor in the form of Joule, right? And that power is I squared R, right? And now I just integrate that. Right? Yes, and there is a back EMF because what happened is there was a battery here. I killed the battery, and then we switched off like this, right? And the current doesn't drop immediately to zero. Right? It takes some time to drop to zero. Right? And that's because of the back EMF. It's resisting that kind of a faster decay. Right? I mean, if there is no inductor, then as I close the circuit, immediately current goes away. Right? Question? Okay. So another way to look at this is also it's this way, right? It's slightly more general.
The back EMF is related to the inductor?
The back EMF is related to the inductor.
Yeah.
Yes. So if I have an inductor, right, in order to build a current I through it, right, this is more general, energy in the inductor. I have to increase it slowly enough, right, because of the back EMF, right? But somebody has to do work, right? A human, a battery has to do work to counteract the back EMF, right? And how much do you have, what you have to do is the EMF, right? It's the minus of the EMF, so it's actually minus, this is the work done. Right, or battery. It's minus the EMF, which is equal to minus d plus dt, right? So it becomes plus L di dt. Okay? This is the rate of the work done, right? So the total energy stored right? Then is an integral of all the total work done, right? Building it from zero current to a final current, right? And that becomes L, integral from 0 to I. This is power, right? This is actually work done per unit time. So, energy stored, times 0 to I, L di dt, cancel, right? I have an integral L 0 to I. I'm missing I something, that's why I wrote here. Right. This is the work done, sorry, I should have looked at my notes. This is the work done by the demon to move one charge, right, against the EMF, right? So at the end of the day, per unit time, the amount of charge that I move, right, is that times the current times dt. Right? This is just dq. Okay. So I have I here. Right? I dt. Sorry for the confusion. This become I r. Right? Okay. So this becomes this becomes 1/2 Li squared.
Where does the DI come from?
The Di,
Oh, L. Oh, okay, never mind.
no, the Di comes from the back EMF, right?
Yeah, I
The
just
back EMF is L di dt, right? And if I want to move a charge against the back EMF, right, then I have to, the amount of what I have to do is L di dt per charge, right? But you know that the charge flowing per time dt is I dt. Right?
same apply.
Right? So the total work done that somebody has to do, a demon has to do, in moving dq across, right, is given by this. Right? So I have this, when I calculate that, integrate all the way from 0 to current I get an energy equal to half Li squared. Is this clear?
Where did the negative from the negative EMF go?
Because there's another negative here because this is the change of flux.
Yeah, so it becomes positive, but there's still the other negative.
Yeah, this is the work done against the EMF. But somebody has to do work
Yeah.
against the EMF to actually build that current. Right?
Mhm.
That's why the money is on. Okay. So let's calculate an energy stored in an inductor. In the solenoid. In the solenoid, L is equal to, what's that, mu naught n squared A over T, right? Is that correct? Yes. Okay. It's L divided by T. Right? Where T is the length of the solenoid. So the energy stored inside the solenoid, if I have current I flowing through it, is equal to 1/2 Li squared becomes 1/2 mu naught n squared A over D, right? That's L times I squared. Okay. Let me do some algebra here. You know that inside the solenoid, V is constant, right? It's equal to mu naught n over D times I, right? Okay, so I can rewrite I to be equal to D naught over mu naught n, right? Just rewriting P as a function of I into I as a function of P. Okay, and substitute it into this equation. Okay, and when I do that, I'll get what do I get? Okay, let's just do it. It's 1/2 mu naught n squared A D times. Did I make a mistake somewhere? No. Times D B naught. Let's call it P is about P naught. Times P over mu naught n After you draw the algebra correctly, you'll get this is going to be equal to 1 over 2 mu naught b squared times a times t. So this is the volume of the solid. Okay. So, and that's the energy stored in the solenoid. Right? Just to draw it, if I have a solenoid. Forget about all the fringe effect. There's current I flowing through it. There's a P field everywhere. Right? Okay. Again, I'm ignoring the fringe effect. Then the total energy stored is 1 over 2 mu naught b squared times the volume. Okay. So if you look at this, right, the energy stored in the inductor, it seems that it's proportional to volume. So the energy stored per unit volume is given by that. And there's an analog to this in electrostatic, if you recall. Electrostatic, with an energy, electrical energy given by 1/2 epsilon naught e squared. Right? And then this is the electrostatic energy stored per unit volume. Right? There's an analog here with B field. Right? If I have a B field configuration, the energy stored is given by 1 over 2 mu naught b squared per unit volume. Right? And the total magnetic, total energy is just an integral of that. I mean, I'm using a very specialized example here to derive this, right? But this is actually general. We don't do a general derivation for this. It's not in Purcell. If you want to look at it, derivation is, as usual, based on vector potential. Then you have to look at Jackson or Griffiths. They have it in there. For the electrostatic case, we derive it more generally, if you recall from lecture way back when, right? But for the magnetostatic, things are slightly more complicated. We're just motivating it to an example with solenoid and generalize. Question?
So if you had like a region of space where there was both a magnetic and electric field, could you add the two completely?
Yes. So if I have a configuration in space, right? Say for example, if I have this is a recall again from our discussion of relativity, right? If I push sigma minus sigma, that's the velocity v, right? Then inside this region there is a p field and e field, right? P field and e field here, and the total energy, electromagnetic energy. It's just an integral of 1/2 epsilon naught b squared plus 1 over 2 mu naught b squared. Okay. I'm not going to talk about toroid. You should just look through Purcell about the derivation on the B field of a toroid. So, next example, we talked about LR circuit. Let's start to build our AC circuit, right? So, the next thing is Well, we did RC circuit before. How about if we have an LC circuit? This is a perfect example for talking about the total energy in an electromagnetic configuration. Suppose I have a capacitor and an inductor. Suppose at time equal to 0, the capacitor is charged. There is voltage V on the capacitor. Right? So Q is equal to, remember, C times V. Right? So at t equal to 0, I close the switch. Right? Close the switch. What happened? Again, current start to flow. Right? And there is di dt. Okay? If I look at the Kirchhoff law, right? Then the voltage here, the voltage drop across the capacitor, right? Which is Q. V is equal to Q over C, right? It's Q over C, right? That is equal to L dr dt. Okay. Okay. But also, what is the relationship between Q and di dt? So the rate of change of Q is equal to minus 1. Right? Because if current is increasing, right, then I lose my charges. Right? dq goes down when current goes up. Right? So let's look at that.
But you lose the charges from the capacitor? Or is it?
Sorry. Yes. So the capacitor is charged. I close the circuit at equal to 0. Current start to flow.
So like huge drop. But do
Yeah.
they
And
do
then
they
you
follow
start
the
to build.
current?
Sorry.
Do they follow the current, or do they just the cues?
Yes, because you have conservation of current, right?
Right.
So if you start to have current, then Q will drop, right? So at time equal to 0, all the energy is actually stored in the capacitor, right? Or it's all in the form of electrostatic energy,
Yeah.
right? And then you close the circuit, current start to flow, and you start to build magnetic energy in the inductor, right? And we want to see what happens next, right? So if I look at that equation, then Q over C is equal to L di dt. Right? But L di dt then is just equal to minus L d squared Q dt squared. Right? I'm substituting I with the dt in the first equation. Right? So what I have then is d squared Q dt squared, right? Let me look at this again. L plus 1 over C, is that right? 1 over C times Q is equal to 0. Okay. This is what happened. This is the differential equation that describes what happened when I have an inductor and capacitor configuration in parallel or in series. Okay. Now, if you see something like this, what do you remember? Simple harmonic motion, right? Simple harmonic motion. Yes. M d And the solution here, the solution of this equation is x as a function of time is some constant x naught cosine omega t plus v. V is some phase that I don't care, right? And omega is given by square root of k over n. Okay? And if you look at this equation, L plays a role of mass, right? L plays a role of m. If I make the correspondence between this equation and that equation, right? If you look, m becomes L, right? And 1 over c becomes k. Okay? So inductor plays a role of mass, and capacitors plays a role of the stiffness of the spring constant. Okay? So here the solution is the same. It plays a role of k. The solution q as a function of time is some q naught, right? But what is q naught? Q naught is just Cp, right? Because this is initially what you have, right? Times cosine. In this case, I know the phase. Cosine omega t. Right? So at time equal to 0, I have q naught. And things oscillate, right? And omega is given by 1 over square root of S. Okay. So charge will oscillate. Q as a function of time will look like this. This is Q naught. The current is just minus dq. You get something as a function of sine omega t. Sorry, I have to rush, right? Then you have something that's completely out of phase. I mean, throw that form, it becomes sine like that. The current is 90 degrees out of phase with the charge. So here is what happened, right? At the beginning, all the energy is stored electrostatically, right? And as time goes by, you start to store energy in the current, right? And this flip-flop back and forth between energy storage in the capacitor and energy storage in the inductor.
That one's I.
This is I, yeah. And it should be drawn the other way. Okay, maybe we should continue this tomorrow because this is kind of important to show the flip-flop between electrostatic energy and magnetic energy.